Everyone, in this video I want to talk a little bit more about finding displacements from velocity time graphs. So up here I got Logger Pro. The vertical axis, remember, represents velocity, which the SI units for velocity, meters per second. And so we're gonna plot the velocity versus time graph for this cart, which will accelerate uniformly or accelerate at a constant rate down the ramp. So let me get that graph made. We'll stop it right there. Okay, so I'm going to draw my time axis here. It's the horizontal axis representing the passage of time. And obviously the SI unit for time is the second. We use seconds for time. We can use other units, but the base SI unit for time is the second. And in the last video I talked about how to find the area and how the area tells you the displacement. Logger Pro has a nice feature where I can actually calculate the area underneath this graph. And it is linear. Notice it is linear. It should be for a velocity versus time graph. And I can find the area. Notice it's now filled in with red. And then it tells me the area up here. And the area, we should know now, is the displacement. It's not distance, it's displacement. In this case, it does coincide with the distance. The displacement is the same distance. The cart was displaced from here to here. The distance covered was from here to here. And so if I find that area, you're going to have to do this graphically on your motion graphs just by calculating the areas of triangles and rectangles. But the simulation here, or the program here, lets me calculate it, and I get a displacement of 0.6025 meters. So here I've showed you that you can get the area. The area will tell you the displacement of the object throughout this motion. Now let's do this one more time. This is what you saw in the last video. I'm going to do this again though, and I'm going to have slightly more complicated motion. I'm going to have motion up the ramp and down the ramp. Just like throwing a ball up into the air, it has a uniform acceleration through that entire motion. And so we're going to have uniform acceleration through the entire motion here. Okay, so let's get that graph made. Oops, got to do it again, sorry. Let's try that one more time. Stop it right there. Okay, so notice, let me change, I gotta change the axis now. Give me 1 second to do that. So my time axis is now right here. Again in seconds. And we're gonna ignore this part of the graph. That's when I was actually causing a different acceleration by pushing the cart. So let's go ahead and zoom in. We'll zoom in so we're just talking about the motion of the cart as it's moving freely. And of course that changes the time axis, so sorry about that. You're gonna have to bear with me here. All right. So let's interpret this motion before we talk about the area. When it starts moving up the graph, that is to your left. Usually that's defined as the negative direction. So we start with a negative velocity of about negative 0.6 or so meters per second. The object slows down anytime a velocity time graph approaches the horizontal axis. It will be slowing down regardless of the direction. So we start with a maximum velocity in the negative direction. It slows down, comes to a stop here where the velocity is 0 meters per second. And this is where it stops and then reverses direction and starts traveling in the opposite direction. Now we're in the positive direction to your right. And so now we are going back in the direction that we came from. We should expect that the displacement for this whole motion is 0. If the car goes up and then it comes back and ends up at its starting point, that is a displacement of 0 meters. The distance traveled would be the distance up plus the distance down. So the distance traveled is not 0. Remember, distance is the scalar, we don't care about direction. Displacement is the vector, we definitely do care about direction. And we should get an area here. If the displacement is 0, which it obviously is, we should get an area of 0. Well, that leads to the question usually, well, I have an area here for this triangle between the graph and the horizontal axis, and then I have an area here between the graph and the horizontal axis. The thing is, and the thing you need to remember, is that this area is negative. Yes, in geometry, you can't have negative areas, but here the geometry actually indicates something that's not just an area. It indicates a physical quantity, in this case, displacement. So I have a negative displacement, which we expect because the cart was initially traveling in the negative direction. So from its starting point, it had a negative displacement relative to the starting point. And then when we go above into the positive velocity values in quadrant 1, the area is then positive, okay? And so anytime a graph, a velocity time graph, it's only for velocity time, is below the horizontal axis, the area is negative. So we subtract those displacement values from any positive displacement values. So here the area is positive. And so I'm going to do that same thing with Logger Pro. I'm going to determine the area between my starting point and my ending point. And I get, there's a little bit, it's not exactly 0, just because I think I caught it before I stopped the timer, but the area here again is negative, the area here is positive, the total displacement here, if I was a little more careful with my conduction of the experiment, then I should get a total area of 0. And if I look up here, the area is pretty close to 0. It's approximately 0 meters. And that's what we expect. We start at this point, we end at that point, the total displacement is 0. Again, the distance traveled would be the distance up plus the distance down, probably about 1.2 meters. But our displacement here is 0 meters because we end up at the same place that we start. So take home point here, when you're using a velocity time graph to calculate the displacement of an object, you must account for any velocities in the fourth quadrant or the negative quadrant. The areas created by the graph will be negative, and the areas created above the t-axis in quadrant 1 will be positive. And so you must subtract these areas from these areas. Sometimes if your answer is negative, then you have an overall negative displacement. So if this was negative 10 meters and this was 5 meters, my overall total displacement would be negative 5 meters, and that would be your answer. The total distance in that particular case would be 15 meters because it would move 10 meters in the negative direction plus 5 meters in the positive direction. And so there's that. And that's about all. Hopefully that makes sense.